Today we're going to talk about mesh generation and specifically how to generate more than 4 elements. So up until now you have been meshing manually by specifying the topology and the coordinates manually. Now that is not feasible when you're starting to get larger models with even millions of elements. So you need some kind of tools to do this. So this is what we're going to talk about today. So for larger problems, you need to a larger model, you need some tools to generate the mesh, basically some kind of algorithms to take a geometry and create elements of different types from that geometry. And what you can do with these tools is also that you can define conditions for the mesh. So, for example, you can say that I want the maximum area of an element not be larger than a certain area. You can also specify the number of elements on a boundary line, for example. So I want more elements on a certain line and less on a different line. And you can also refine the mesh that you have generated by the results of your calculation. So if you see that there is a large gradient somewhere around corners, for example, you can use the input from the last result to refine the mesh at certain points. This is not something we're going to do in this course, but it's good to know that that option exists. There are 2 types of mesh generation you can use. The structured mesh generation, that is, you have some kind of rule that defines the mesh. Have a coordinate system to kind of reach different nodes, rows, columns, etc. So you know that if you go, so there is an element at row 2, column 4. So there's a rule to get to that element. In that case, you have pretty good control over the element generation. You can say that at a certain side of the mesh, you can have a certain number of rows and less on a different part of the mesh. The second method of generating meshes is something called unstructured mesh generation. And in that method, you define the geometry, basically what you want to mesh using the same geometry, and then you tell the algorithm to fill the domain with elements. And usually this is limited to triangles or tetrahedral elements. But the basic element for starting the unstructured mesh is usually the triangle or tetrahedral. Then you can combine the elements together to form quadrilateral elements or 4-node elements or 8-node elements. So an example of an unstructured mesh looks like this. You can see that you have triangles, and you have also points added to inside the geometry on the boundaries that have been added to the geometry to create the elements. On the right example here, you have an aircraft wing, and then you have the elements generated around that. So basically you have a boundary, and then you fill that boundary with fill that area with elements, and that is the purpose of the algorithm, is to do this. Structured meshes, you can see almost that they are structured because there is a rule in the visual rule that you can see here. So on the left side here, you can see that there are number of rows here, even if there's a curve here, the same number of rows here. Then you have a columns here that goes around here, but you can always go, I can find every element by a rule. So I can go 3 columns to the right and 3 rows up, and I can find this element here. You can set the density of the mesh by specifying the points on the line here. So I can say that I want more elements here or here, and then the algorithm can generate more elements there. And you think you can be limited by using structured mesh generation, but it's kind of a way of using super elements to build your geometry. So in this case, this is a tunnel opening, half of it. So there is a symmetry line here on the left side. And then you have this four-sided super element to build up the structure here. The important part here when using this that the connecting lines here must have the same number of elements to be able to be compatible. But you have very good control of exactly how the mesh will look like using this kind of approach. In this course, we are going to use a software package called GMSH. You will not use it directly because we will use it through CalFM for Python, because CalFM Python has built-in support for using this tool. So it's a three-dimensional finite element mesh generation application. It can also generate 2D, which we are going to use in this course. It's also standalone application. So you can, if you open a command prompt and type GMSH, you will get the user interface for that application. It can also do, you can model in that application, so you can create geometry and then create mesh, and also there is a interface to solvers as well. And it can do both structured and unstructured meshes. It uses a geometric description language to define the geometry, lines, circles, splines, and surfaces, and so on. And that is in language. And what CalFM does is to generate that description for you. So you call functions on an object to define the different lines and circles instead of specifying them directly in that language. And when you are done with that, the mesh generation in CalFM will automatically call Gmesh on the backend. So, as I said, CalFM uses the Gmsh underlying mesh generator, and it's implemented in the calfm.geometry module and the calfm.mesh module. So the geometry module is where you create your geometry object, and on that object you will also create, you add your geometry to that object, and then you pass that along to the mesh generator, and it takes that object and generates the normal EX, EY, EDOF, and so on, those variables that you need to be able to assemble your finite element model. And then you create mesh, and then so what you get out of the mesh generation in CalFM Python is the normal arrays that you have used until now. So if you have created a solver now for your worksheet 2, you can use the core of that solver to take the same data that's coming from the mesh generator, plug that in. The loop will, of course, be looping over much more than 4 elements, or perhaps even 10,000 of elements instead. So I will do an example here. It's very similar to the one you do in groundwater modeling. So this is the geometry definition for the groundwater problem. So what you see here is that we have a model that is defined by W for the width, H for height, and T for the thickness of the slit, and then you have D, which is the depth of the slit. And these are not element coordinates, so these are geometry coordinates and lines. So we have coordinate 0 here, 1, 2, 3, 4, 5, 6, 7. And then we have the lines here. We have 0, 1, 2, 3, 4, 5, 6, 7 here. So this is the model we're going to build in code. So the first step we need to do is to import all the modules we need for this task. So we will use CalFM core, which you should have start using in worksheet 2. We import that as CFC. We import calfm.geometry as CFG. CalFM mesh for CFM, that is the meshing support. This MPL for the visualization function as CFB, and then CalFM utils for some other stuff that are good to have functions. And of course, we also need NumPy. We set up the problem parameters. So we're going to create a parametric model. So this is good when you put the parameters in the beginning, you can change those parameters later on, and the problem will change. Yes. Next, we need to create our geometry object. And that you do by creating, assigning a variable j for geometry. And that is an instance of cfg.geometry. So geometry is a class, and we create an object j that will contain our geometry. And then we just call multiple times here, each for every point in the model. So we have 8 points, and we call them g point, and then we give a list of coordinates. And then we just continue on. You can see that we define everything with the parameter, geometry parameter we defined before. Next, we define the lines here. In this case, we will, if it says splines, it will be a line. And then we just tell it the line should go between the points 0 and 1. 1, 2, 2, 3, 3, 4, 4, 6, 5, 6, 6, 7, and 7, 0. So 7, 0 goes back to the original starting point again. Then there is a special here, it's called marker 80 and marker 90. And what we need to have when we are solving a problem, we need to kind of identify from the geometry which degrees of freedoms are in a certain position in our model. So if we go back to our, you can see here that we have, let's see here, it's said 2 to 3. So that is the line 2 and line 6. So line 2 and line 6, here we want to be able to apply the pressure. So the pressure levels should be different on the different sides here. So we need a way to identify these lines in some way later on when we define our boundary conditions. So just remember 6 and 2. And we say that, and marker here is a way of, you can set any number, what you want, you can decide yourself. We just put 80 and 90. So that is the line 2, and this is line 6. Then we have to tell the mesh generator what is the surface we want to mesh. And what we do then is we give the lines continuously around the geometry. So 0, 1, 2, 3, 4, 5, 6, 7. That defines our surface to mesh. For those that have the temperature problems, you can also define holes here. So you can create of course, lines that describe a hole, and then you can tell the surface command here that there is a hole. Next, we need to define some properties of a mesh generator to define what kind of elements and what kind of how many degrees of freedoms we have per node. So we just create 2 variables here because we know we need to have them later on. So I define them as variables here. And then you define them as properties of the mesh generation object. So you can see here that I create a mesh generation object here by taking my geometry and giving it that as input when you create the mesh generation object. So now the mesh generator has the geometry to stores it inside the object. Then we give the element size factor, the element type, and degrees of freedoms. And the element size factor here is the maximum area of the elements that is allowed to be able to create. So if the elements are larger, it kind of adds more elements to the model. And then finally, you call create on the mesh generator itself. That will, then you have to have chords, EDOF, DOFs, BDOFs, element markers here. All of these have to be on the left side. So when the mesh generator has finished, it will create a coordinates vector array, an EDOF array, DOFs array, and BDOFs array. So the DOFs are degrees of freedoms at the nodes. Boundary DOFs, that are the degrees of freedoms on the boundaries. So, for example, you have the markers here. You can go BDOFs, bracket marker, and then you can get all the degrees of freedoms that is on that marker. marker line. Next, we need to determine the number of degrees of freedom. So in this case, because we do use a mesh generator, we don't know how many degrees of freedom we have generated. So we need to calculate, and we can use to check the size of the DOFs. That will give us the total number of degrees of freedoms in all the nodes. So DOFs contains, there is a DOF entry for every node it has been generated. We also need to create our EX and EY arrays, and we can use the chord extract command here that takes the EDOF as input and chords and DOFs, combines them together and creates EX and EY arrays. Next, we need to create the global stiffness matrix, and we do that by creating a zero array by end of size and calling it K. And now we can use the same approach as for the worksheet 2. We loop over EDOF, EX, EY. So that will mean it takes one line from EDOF, one line from EX, and one line from EY, and assign them to LTOPO, ELX, ELY. And those we can use to call the element routine. You can see here that we created KE matrix by specifying ELX, ELY as the element coordinates. EP and D are defined on other places in the beginning. And then we use ASM to assemble the element matrix into the global stiffness matrix by the topology here. This is the assemblation. So we're kind of getting there. Then we have to assign boundary conditions. And boundary conditions, because we have now elements on a line, we need to kind of know which degrees of freedom we have on a line. We also need to specify the F vector is kind of simple. It is just NDOS, 1. The BC is the degrees of freedom that is going to be prescribed, and BC val is the array of the values that we are going to prescribe. And to make it easier for you to do this, there is a function called apply BC that can do this assignment for you. So in this case here, we have two boundary conditions we need to apply. F will be 0 here. We're not extracting any flows. We are just going to solve the stationary condition here. So we have 80 as the marker. We're going to put on this, we're going to say that there is 0 pressure there, and there is on 90, we have 10 meters pressure on the 90 marker. And that will modify these variables here. Now we can solve the system. So we can call Solvec KF BC BC val, and then we get the displacement and the reaction forces. Next step, we need to extract element displacements. We do that using the extract LDISP command in CalFEM. ADOF as input, A as the parameter here, which is the displacements. And then we have that array. And then we are going to calculate the max flow of every element. So we create an empty list here, and then we loop over the range of elements here. And then we call the flow to I4S with our element coordinates, EP and D, and EDI, colon. We could have done that with using zip as well, but in this case, we need to append here. So we append the max flow to each. We calculate max square root, and then we add that to this max flow array. Next, we can visualize our model here as well. So we have see if a figure, draw geometry. You can see there is a special command for drawing the geometry. We have draw element values. We have draw mesh. And there are many parameters here that you can specify to control the layout of your plot. You have draw nodal values, and we draw color bar here as well. And then if we are running it standalone, you need to do show and wait at the end here. So if everything works, you should get something like this, and the max flow. So you can see the max flow is on in this slit on the bottom here, because it flows from the higher pressure to the lower pressure, and the most flow is on the right, that's closest to this slit. So this is what I wanted to show as a slides here. Now I'm going to switch to live mode here. So all of the examples I'm going to show you now are part of the in the GitHub repo for Colfim in the examples section here. So in the first example, we're going to do a very simple triangle. So you can see here I import all the stuff I need. Then I have to create my geometry object. And on my geometry object, I create my geometry. So in this case, I start at 0, 0. I go x5, and I tell it should be marker 20. And then I go 2.5, 4. So that is the mid-low. So it's going to be a triangle. And then I say that I have a line between 0 and 1. I have a line between 0, 2, and I have a line between 2 and 0. So I go back again to the starting point, and I call this marker 10. And then I do surface 0, 1, and 2. I create my mesh object here, like this. I pass my geometry to the mesh generator. I tell it I should have what kind of elements I need, what kind of degrees of freedom we have. So for the temperature and the groundwater problems, we have 1 degree of freedom per node. For the stress problem, we can also generate 2 degrees of freedom or more. Element size factor, and I'm going to show you how this will look when I run this now here. So if we run this, you can see here now I get 2 windows here. One with the triangle here. This is the geometry. And this is the mesh generator. So you can see at the end I do draw geometry, and then I do draw the mesh here. So let's try some things here. So what happens if I change the element types to 4 node elements, and I run this again? So now you can see here that I get 4 node elements, and this is something you have to be careful with mesh generators, that sometimes it can't solve the problem. And you can see here that I get some jacks in the element, not the proper mesh. Let's see if we can, by scaling it down a bit, see if we can get it completely working. Almost. There's something staying. I'm not completely sure why it doesn't do this here, but you get the idea. So the mail set function that changes the number of elements. And this is what elements you want to generate. So now I go back to triangles here again, and you can see you get the triangles here. And if I specify a really large element size here, like 0.05, you can see that I get larger elements. And you can also see here that I have specified markers here, and I print out the boundary DOFs, and you can see here in the printed output that it's a dictionary here, and you have the marker here, 20, then you have marker 10, and these are the elements of the different so you can, if I want to have I can print out, let's see here. I go down here and then I do BDOFs, and I want to look at the marker 10. That's a line. And if I run this, you can see here that I get all the degrees of freedoms that is associated with this marker. if I go boundary DOFs 2, in this case here, L20, you can see here that this is a point, so I should only get 1 degree of freedom here. So let's see if that works. Oh, I have to close the windows here. So you can see here that I have only a single degree of freedom here. So boundary DOFs is a way of assigning degree boundary conditions to your models. Okay. But it's a dictionary where the key is the marker. Okay, so let's go to the next one. So here I have a more complicated example with 2 degrees of freedom. In this case, it's a stress problem. It's a beam. It's 5 meters long, 1 meters high. Thickness is 0.2. Some other parameters here. And then I can see one thing that is a good idea is to name your markers. So instead of specifying the numbers in the directives, I can specify here left support, right support, top line. So when I define the geometry here, instead of using the numbers here, I just do marker left support, marker right support. And then you can see marker top line. And that is more easily read when you are looking at your code. You can see later on that how much when you're assigning boundary conditions, you can see okay, that is the top line I'm assigning now. So then I create a mesh. I use 4 node elements. I use 2 degrees of freedoms per node, maximum element size of 0.10. I call my mesh generator create, and then it will return me all the CalFem data structures I need to do my solution. So you can see here I calculate my numbers or total number of degrees of freedoms. I create my EX and EY arrays. I create my global stiffness matrix. And then I loop over and create my elements here. So, and then assemble them into the global stiffness. And here I create my force vector. I create my boundary condition vectors here. And then I apply the boundary case. And here you can see I assign apply BC to the left support, to the right support. And here you can also, if you have when you only have a single degree of freedom each node, you only specify the first number here. The second part here, the second parameter here is the degree of freedom you want to assign. So you can say dimension 0, that means that I assign, we go down here, all. So in this case, both degrees of freedom are assigned 0. 1 is in X direction and 2 is in the Y direction. So in this case, I assign both degrees of freedoms in that node to be 0. And for the right support, I only use in the Y direction, so it can roll. It's a beam. And then I do F here. And then I apply force total, which is a method that applies a total force to a line, in this case 10 here, and then in which direction, so X and Y, so in the Y direction. I solve the problem, I loop over, extract my element degrees of freedom. I have a von Mises here list, and then I append all the von Mises stresses here, store them in von Mises here. So if you can see from these examples here that it's a lot of the things that you need to do in your worksheets. So please have a look at these examples. Those are on GitHub in the examples folder. So let's see what happens if I run this example here. So we look at the geometry. So you can see here you have 0, 1, 2, 3, and then 0, 1, 2, 3 lines here as well. And then you can see the mesh here. I have quadrilateral elements. and we have deformation figure here, and we have the von Mises plot here. Now I haven't, I should have put some color scales here, but I have not. So you should always do that with diagrams, but you get the point here. So just look, we can look at the visualization functions here as well. So you can see draw mesh here. You can see that I put in all the variables we created from the mesh generation. Draw element values. These are, in this case, it's the displacements. That is the node values. So you can see here that draw elements, draw undisplaced mesh is false because we also specify the displacement array here. No, sorry, we don't draw element values. We just draw the degrees of freedom here. Draw displacements here is it's what we draw the displacements with. Yeah, so you can combine these because we have A here. You can also have the displaced mesh in the element values plot. So you can combine the different things here depending on what you want to visualize. So that was that example. Now I just show you that you can do a lot more advanced geometry as well using splines, ellipses, and arcs. So in this case here, I have a much more complex geometry, a lot of points, and we can use different commands to do curves instead. So here we have an ellipse, and the parameters is the start and center, major axis, and end. 7, 8, 9, and 10. So you have to specify a lot of things in to create a half circle. And then you can do splines. And if you just specify 2 coordinates, it's a line. If you specified more than 2 points, you get a spline. And here you will also use the feature that you can specify holes. So in the surface command here, you can specify the first part here is the outer surface, which will have holes in it. And then you can specify here a list of points that will be, let's see here. Curves that will define the holes. So the first part is the surface, the other ones are the holes. If you look at the command here, you can see you have outer loop, that is the surface, and then we have holes parameter here. And then we can mesh this just like we did before. So if you run this here, you can see that we get a quite more complex geometry. So you can see that you can actually mesh quite complex geometries and create a lot of elements for this. So you can see that you have an ellipse in this part here. And we have a closed spline here consisting of 3 lines. That was that. The flow model, I think we went through in the lecture. Yes, so this is a more complex stress-related example. And in this case, we have 2 material areas. So we have 2 areas in the same model that has different material properties. So in this case here, we have E1 and E2, and we have D1 and D2 for the D matrices for each of these areas. And we define markers E1 and markers E2 here, and markers for the boundary conditions. And we do some handling here to be able to loop more efficiently in the code later on. So we build up a model. It's 2 squares, and there is a middle area inside that is smaller that has different properties here. So you can see here that this just builds up the geometry. We've specified that we have where we have our load and fixed boundary conditions. Then we define a surface here that is the outer surface, and it has a hole. And then we have a inner surface here that is a hole in this part here, but it's a internal surface of the property, and we give it a marker E2 and marker E1. And then we can mesh this, and we can use this here to get element markers here. So this one here will contain a dictionary of the elements that is part of the different markers as well. So BDOF is the boundary degrees of freedom, and these are the element defined by the markers. And then we just do an if statement here. In this case, no, sorry, we have a element marker here that defines which marker is currently for this element has. And then we just select the element properties here depending on which marker we have. And then we loop over calculate element stresses. Of course, we need to use element properties here to define which element materials we have in the different sections here. Calculate aphomesis stresses, and then we display everything here. So let's see how this can look. If we look first at the geometry here, so this is the geometry we have. We have an outer area with one material property, and then we have an inner one with a different material property. And you can see here that you have how it looks when you combine them together. So it meshes together, and they are connected together here in the mesh. And here you can see the displaced mesh here as well. Here is also a much more complicated mesh here. It's a testing body here with an indentation in the middle. And it's also some calculations here because we need to define the points at certain positions here. So we use a special parameter for this here. But there's a lot more coordinates. And here we do loop over here to create the points. We have all the splines. And we create curves, circles, structured surfaces. So this is actually a structured mesh. It's not an unstructured mesh. So just let's see how this looks like. So you can see here that we build up the geometry using these kind of super elements. So these are four-sided elements here that are connected together in different ways, which then creates this kind of mesh here. And if we look at how it's defined, yeah, you can see here that here you set elements of curve 10. That defines the number of elements on that line. And we think we did the same thing here with the splines here. We add how many points that will be used to divide up in the number of elements on each of the lines here. And that determines the element. So if I do, for example, 5 here instead, you can see here that I have less elements here. So let's break until quarter past. And then I will go through an example, a bit more complex example that is more similar to the problems we are going to do in worksheet number 3. So I pause the recording here. So for the final part of this lecture, I will go through an example and convert it to the model that you have in worksheet 2 and 3. So using classes for model params and the solver and for the results. So what I'm going to do now is to use the example 7 here in the problem mesh manual. And I'm just going to run it here to show you how it looks like now. So it's a temperature problem. Kind of a pipe piece here. It's a curved structure like this. And it has 2 different areas of conductivity. So it's high conductivity here and low conductivity here. And we are going to do a parametric model of this. So you can see here that I have first part problem constants here. And this is the things that will go into model params class. So I created an empty project here, defining up just the skeleton classes here. So I defined a temp model params class that will store all the parameters for a problem. It has a property called geometry or a function called geometry that will return the geometry of the problem automatically. So I've added that to the model params, but I think the geometry belongs to the parameter class. And the idea of having geometry there is when you change the parameters of the model param class, it will automatically, when the mesh generator calls on the geometry, or the model solver calls on the geometry, it will always have an updated geometry. Instead of just assigning the geometry attribute, I call a geometry that will generate the geometry for us every time. So just let's start moving over the parameters over to this function here. So I'll go in here and I just do like this, copy, and I go back to my model here. And where I have pass here, you can see I told you about the most useless function in Python called pass. And this is where I have it because I wanted to have a class that works but doesn't have an implementation. Then you have to have something, at least one statement. I paste that in here. And now I have to do the indentation a bit better here. This. And for this to work as a class, we can't just use the variables names like this because those are only active in that method of the class. So in this case, we need to make them attributes of the class, and we do that by adding self to them. Then they will be created when you create a new object that will have a kx1, ky1, and so on. So I just add this to this one here. The D matrices could be considered to be moved to the solver, perhaps. We can skip this for now. It's a design choice you can do if you want to. And then I also have to, you can see here that because I do need self, now you have to do self in front of all the variables here as well. Self dot, like this. Indentations was wrong here, like this. So that was the parameters. And we will do, we need to have the geometry generation function as well. So we go back to our model here and we go down to the geometry definition here. This must also go into the model. In this case here, we don't have to, as this is a function that will return the geometry, we don't have to specify self.j in this case. We just create a temporary j here, which we'll use to access the points here. And now we see here we need to move the markers as well here. Let's see. Oh, we can skip that. So we defined up the models, and then we do, we'll remove this here. We don't have to. And then finally we return J here. So we create J here and return it out here. And notice also that I added the property declaration here. That means that I can access the geometry function as a property. So I will just show you how we can use this in our code here. So I'll just comment out here. We can do geometry equals to model params geometry like this. You can see that I get back a geometry object here, and that is our object containing our geometry description. And every time I change a parameter here on the model params, so if we do model params kx, you can see that there are part here, and we do 100 like this. When we call the geometry here, it will automatically generate all the stuff for us. If we change the geometry, it will automatically reflect it here. We could have, of course, also in the model, the temp model here, define variables here defining the geometry here if we wanted. Now the model is fixed in space here, but you could also have parameters for your width and height and stuff like that that changes the points here. But we don't do that in this problem here. So now we have a working model params class. The result class we can leave empty because we will assign the results from the solver itself. So we just have an empty class here. You can, of course, add your result names variables here as well. I think that is done in the worksheet here, but you can also leave it out and then we add it later on. But we need to create a model solver object, and the model solver depends on two things. It needs the parameters that we define for the model. So we need to give it a model params object, this here, and we need to give it model results here. And we store them inside our object here. So the model solver will have two references of the model params object and the model result. We store them inside just to make it easier to use it. Then we have an execute method that will execute the calculation. So the code for that is available in the column example here. So I will go through here. You can see here, after we define the geometry here, now the solver code starts, or the mesh generation code. So the code here, we copy over. Until we skip the visualization part here, we just keep the code that does the computing. We go into the empty model here and we replaced our pass with our pasted solver. And now we have to indent this so that it's part of the execute method. L type and DOFs per node, these are local variables. We don't have to, those are not, we don't have to define them as attributes if we don't want to. It can be useful now if we want to have them, store them in the result output. So the visualization routines knows about this, but we will do that later. So first we can see here that we have a J here, it's geometry. So in this case, we need to give them our own geometry. So in this case, we do self.geometry. So no, sorry. Model params geometry like this. So we the model params contains the geometry, and we call you can call it as a function, or you can just use it as a property here like this. And we give L type, and we get the cores, DOF, and EDOF, and so on. Then we assemble our problem, and here you can see here already where we're missing EP here. So what I'm usually do to make it easier to handle all this stuff, you don't want to specify self.modelparams.something. So what you do is you here in the beginning we do what we had EP. So we do stuff like this for the variables that we need here. So dict, that is the D matrix dictionary that we were going to use. And we define them just as simple variables here. And this is, you can do that because EP points to the same memory location as EP, but you don't have to write all that extra stuff here. Now we can refer to EP as just EP. And you can see it, there is no errors here. So now we have created our solvers. We need to compute our element forces. We do this here. Now we need to, let's see here. Where did we define our? There we have. Yes. So what we need to do now, we need to figure out what goes into the result class. So now we have done our computations, and we need to transfer all the results to the model results class. So our AI friend always suggests what I need to do here. So we need to pass over the displacements, of course. We need to display the reaction forces, the element displacements, coordinates, EDOF, mesh, if we want to do that, element markers. And the mesh object we don't need to take over. Element markers could be, we also don't need that. Everything we need to get back from the code here, and perhaps also self model results .es. Now we need to, we haven't done that here. Okay, we skipped that for one. But in your example, you also need to store the output from the flow, the element forces somewhere, and that should also go in here somewhere. So I do that self.model results. Something like that. Just fix. We don't use it here, but now we have assigned all these results to our model results variable, and that is the output from the solver. Already now we should be able to do our solver. So let's see here. We create a model results, and we create a solver, and let's see if it works. So you can see here that I pass over model params, which we created here, and model results. We can skip the printing here. And let's see here if we can do print model results. We just print out the reaction forces here like this. So let's see if I have some errors in my code. Oh. So you can see here now that we have completed our solution and we have results here in our result vector here. So you can see the idea with the model params and models is kind of decoupling the connection between the input parameters and the output parameters and the solver. So the solver doesn't know, just needs those inputs, and it will store the results in the model results object, which you can use outside of it. So the solver itself doesn't store anything. It just kind of takes input and stores output. And the idea with this is later on when we do a parameter study is that we can use this to create multiple parameter sets and also multiple model result sets when we solve. I will show that later on as well. I have created here, just to kind of make it quicker, a temp model visualization class. And the visualization class also depends on the model params and the model results. So we do the same thing as for the solve. We store those objects inside our object, and we can use them to make it easier to visualize things here. So we just uncomment this here. And then we can call show geometry, show mesh, show temperature, like this. Let's see if it works. Okay, we need to specify the meshes here as well. So let's see here. So now you can see here we have created an object-oriented version of our problem. So what's the point of all this? You could have just made a simple temperature solver that we had here in the model example. So why make it so complicated? Because now I'm going to show you the real benefits of this. So I'm going to look at separate model here. It's just, so what we're going to do now, instead of calculating for a single value, we will create a range of values for the kx property, for example. It could be anything. And we will create first the values here from 10 to 100 and 20 values between. So we will do 20 calculations for the same thing. We will create a list of parameters. So this list will store model objects, model param objects. So each parameter set for every model we want to solve. And then we will also create one temp model result object for each calculation. So what we do here, we do for value in kx range. We create the model params, model result. We change the value. This is the important part. We change one of the values here so that we want to see the effect of. And we append the parameters and the results to the model result, these lists. We loop over here for parameter result here, and we execute the solver. And you can see here that what we loop over is the parameters and result lists. And we give them as parameters here to the solver. The solver execute, it will take the parameters, store the results in the current result item here in the loop. And then we can loop over the results here. So for example, we can see how the temperature varies at node 50 over time. So let's see what we can print out. You can see here. We print the parameters here every time we run the example here. So you can see now we loop over, we do all the complicated assemblation of steps, and now you can see here that what happens when we at this position here. So you can see the temperature is changing. So that is the idea with using these objects here, is to enable you to do parameter studies, which will be part of your assignment as well here. So in worksheet 3, I think there is a parameter study assignment, so that you will vary one parameter. It could be, for example, for the groundwater problems, you vary the width for the slit, and then you loop over that and change the width and see what happens. So that is what the idea is, and that's, I mean, this is really compact code here. You don't have to. It's a complex solver, but it's really easy to vary the parameters because we have encapsulated everything in different classes. The parameters in one class, the temperatures, the results in one class, and then we can just loop over them here, do another calculation, and so on. You could, of course, do this in a single loop as well. I think it's a bit too complicated, but you get the meaning here. So that was what I wanted to show today. I hope that you get a bit more insight on what's coming in worksheet 3. And it's also a good idea to, as I said, I start with just a Calfem code, and then I convert that step by step into the worksheet 3 code with the classes here. Okay. Any questions?